Okay, so actually I've given this talk a couple places, and actually because we're in a live situation, I'm going to just kind of show some of the software that's behind what I want to talk about. Not because I'm trying to show off the software, but just to talk about, it'll give you better context of what's going on here. But this is something that hopefully will come out at the beginning of the year. It's we're building this for Dex.com, and this is a deck designer, and all of this code is live JavaScript in the browser. As you see, we're designing a deck. I can turn off the decking, and you see as we drag that along, new joists are made. If it's long enough that it needs some kind of extra support, it does that. You can switch to a front view, and you'll see those. You can switch to a 3D view and see that. And this is all happening live, and JavaScript's happening right there in the canvas. I can take that and say let's add an octagonal piece of the deck, and I can attach it like that, and it'll just build it all together. Or I can say this is going to be at a different level. I can actually switch to the front view and change it if I want, but let me make it a little bit smaller here and say, well, now that I've done that, I need some stairs, so let's put some stairs in here. And again, you'll see that as I switch to my 3D view, you see that the stairs are actually going there. And when you're done and you like your deck, you can say, let me see what I need to order. And it'll show you all the hardware, the lumber, etc. you're going to need. And when you decide, okay, I want to build this, and because our government is very interested in your permit, you can download a permit-ready plan which follows all the industry codes, and will show you exactly what you need to do, where the footings go, how deep your footings need to be, etc., etc. So every single ounce of this is built in JavaScript. And now I want to switch and talk about how do you go about building something like that. So let's talk about object-oriented JavaScript in Canvas. And this is actually something, everybody's writing JavaScript in some way, shape, or form. But a lot of them are using it in lots of different ways. And actually JavaScript is kind of classified as a prototype-based scripting language with dynamic typing and first-class functions. This mix of features makes it a multi-paradigm language supporting object-oriented, imperative, and functional programming styles, which is kind of interesting. A lot of people use JavaScript and don't know what any of those words mean, right? But I came from a world where object-oriented was kind of important, and if you're going to build a system that has any kind of, it's not just a bunch of scripts, you might want to think about the object-oriented style. What a lot of folks don't realize is that underneath a lot of things that are out there that you can do in JavaScript, there's this canvas element that's part of HTML5. And it allows for dynamic scriptable rendering of 2D shapes and bitmap images. It's a low-level procedural model that updates a bitmap and does not have a built-in scene graph. Okay, so basically what it is, this is the primitive about what a whole lot of other stuff is built on top of. SVG is actually built on top of Canvas. There's a few other things that are built on top of Canvas. But a lot of folks don't even know this thing exists. And it's actually a pretty full-functioning graphics library that you can do lots of cool stuff on the screen. So the whole idea of objects, really kind of came from the mother of all object-oriented languages, the Smalltalk language, which this Byte magazine article, if you were around in the 1980, 81, you probably read this magazine article, and it was a buzz for many, many years. And everybody says, well, that's all cool. That would be great if programming was like that. And it took many, many years before people actually got it out of the labs. And actually, I was one of the first people that got to use Smalltalk for a commercial product. And during that time, I met these two guys who some people know, Kent Beck and Ward Cunningham. These guys were actually one of the first folks out there who said, you know, we're going to, even though they're working in a lab, they were ones who said, let's make this practical and build real stuff with this. That's not just for research, but, you know, out there. And really started reflecting a lot on how do you build good object-oriented software. And a lot of folks now, they just get taught, hey, here's some software. Oh, and it's got object-oriented stuff. Use it. And no, I haven't really been taught about, okay, what are the foundations of this thing? But one of the things that Kent and Ward did, they had a really pretty nice job that they would go off and do consulting within Tektronix, but then they'd have a little week of downtime. So they said, what are we going to do this week? And they'd come up with a project to do from the beginning of the week to the end. And one of the things they did was in the late 80s, they were working there and Mac Draw came out. This was, again, late 80s, the little Macintosh, right? And there was a drawing program on it. Everybody thought, oh, this is the coolest thing in the world because you could never do this before with a computer, at least not one that you could bring into your house, right? And so they looked at that and said, boy, I wonder how I'd want to build something like that. So they spent a few days building a drawing thing in Smalltalk, and within a couple of days, they were, man, this is really hot. So they started calling it HotDraw. And then they started talking to people about how they built it. And Ward joined Knowledge Systems Corporation, which I was a part of in 1989. And what happened is he just kept, because they could build this thing in a week, it kept getting rebuilt in a new version of Smalltalk. Or somebody said, hey, you know, I wonder if you could build this in Java or whatever. So there's a lot of things out there. It was kind of a research project that became kind of a little cult following, I guess, in some ways. But, you know, over time, a lot of different people did HotDraw. I did one in Java. I did several of them in Smalltalk, in different versions of Smalltalk early on. But one of the things that I found, I was always working in a place where I'm building software for people, not just for the fun of it. And I said, well, there's all kinds of ways that you want to do direct manipulation, right, of something, right? And the deck is just one example of that, right? There's a lot of ways you want to do, everything's not a CRUD app. Everything's not just, you know, you stick in data and register and, you know, get an email later, right? And not know how to get off of people's email lists. But the good, the bad, and the ugly of HotDraw is, you know, this was and is actually a very simple and powerful drawing framework, conceptually. And since then, there's many other frameworks and libraries for drawing, right? So when I have a project, people say, well, why don't you just use this thing? Or why don't you use that thing? Well, the dirty secret is most of them aren't built with an idea that you're actually using it for an underlying application, right? They're built, oh, here, you want to draw stuff? Great. Well, I don't want to just draw something. I want to do some manipulation of things that actually have some semantic meaning, right? If I'm designing a deck, I want to be able to have joists and stuff. I want to be able to print a blueprint, right? I want to be able to do things like that. So there's many applications for direct manipulation of drawings outside the domain of drawing. And most of the drawing frameworks, even the open source ones, are really about, here, cool, draw stuff, right? And of course, depending on the domain, the kind of things you want to draw are going to be different, right? So how does one apply the direct manipulation of drawings to an underlying domain? And another thing is, how do you even test it? Because as many people who've messed around with graphics always find out, how do you test that your graphics are working, right? You test it because somebody looks at it and says, that's not right, right? But that's not really very satisfactory when you're trying to move forward and have a regression test and make sure you didn't break something, right? So how do you test those things? So over the last few years, we've had the privilege at RoleModel Software of building a few different systems where we had the idea, hey, we had to do some direct manipulation. So we did one for the Friday Institute where they were building an educational framework for teaching mathematical concepts, and they wanted to use direct manipulation to make sure people got the concepts. And so it wasn't just that they were doing cool stuff here, but and I'm not going to show this whole video because interest of time, but the bottom line is they're manipulating things and seeing how does this person divide this, and it's not just doing it, but we're monitoring what are they doing. Are they getting the right answers? If they're not getting the right answers, what kind of other educational things might they need, right? So it's not just, hey, cool, I'm drawing a picture. So what kind of picture are you drawing? You got a problem to solve, right? And there's a lot more to the domain than that. And of course, Dex, you just saw, I'm just gonna flip through this because you saw it live. So if you're looking at something like that, how do you approach this? So what's interesting is on the Ward Cunningham's original wiki, there's still this original CRC card diagram of HotDraw. And this is what he did in the 80s and wrote it down, right? And if you look at that, it's a very simple description. But you know what? We've moved since the 80s, right, to all the stuff we have today. Back then, the internet was a place you maybe, if you knew about it, you might send email over it, and that was it, right? You didn't have what we have today. And pretty much when you were drawing something, you were drawing directly to your screen, right? And you had to install your software. What does it look like today? So I want to look at just the general concept and say, how would you do this if you're building a system that's distributed over the internet and working in somebody's browser, or maybe working on their smartphone or whatever, right? So we look at the whole idea of a drawing, and drawing's really a simple concept, right? It's in some ways saying it's the model for what you're doing, right? And this drawing just has a bunch of figures. And you can add and remove figures, and when you draw the drawing, it tells all the figures to draw themselves. Not real complicated, right? Take another step further, and we look at the view. Well, guess what? Today's view, it's just this, right? I've got a canvas with a drawing, right? And this is an abbreviated HTML. This is a slim or something, a JADE file, right? But I've got a canvas, which is a drawing, and that's my view, right? That's it. That's what it is. That's what I get to work with. And then the controller, well, what would that look like? Something really simple, right? This is really the idea that you get a drawing, you get yourself a canvas, and when things happen, you tell the canvas to draw itself. But you don't only tell the canvas to draw itself, you tell the drawing to draw itself, right? And that's really it. And then you can mess around with the scale and a few other things to make that happen. But the drawing controller is just saying, oh, you did something, redraw, right? Or redraw a section, or redraw it at a particular scale. So you just go build yourself a simple controller and hook that up, and we'll look at that in a little while, how that hooks up. But then Ward goes on to say, okay, what's the next level deep? What are these figures? All right, so drawings hold figures, and he had an abstract class of figure. And so as I've looked at that over time and implemented HotDraw a few times, I said, you know what, figure's probably not the right word. We just want something that can draw itself. So we came up with this idea of a drawable. The drawable basically just has a couple different ideas. You can give it properties, which might be the background color, the foreground color, the pen, whatever it might be. And in the case of Canvas, there's a whole bunch of things that you're setting into properties. You say, oh, I am going to draw on this foreground color or whatever. So you can just set a variety of properties in it, and you tell it to draw. And before it draws, he saves the context, sets up the drawing context to have those properties, and then draws. Pretty simple concept. And you can go into start doing other things, like maybe have a polygon figure, and a polygon figure just does the same thing. He has a bunch of vertices, and he makes this thing happen, and these are just calls to the Canvas library, right? But as soon as you start coming up with all kinds of different figures, some are polygons, some are not, pretty simple, right? You can draw lines, have a line figure, text figure, whatever, then all they do is just draw themselves on top of the canvas. So moving on slightly further than that, the controller collaborates with tools to make changes. And you might have a creation tool, right? If you say, oh, okay, every time when I have the creation tool selected, I want to stick something on there. Or you might have a selection tool, and a selection tool would select a figure or whatever. So we actually did come up with an abstract prototype for tool that he just knows how to activate itself, and the tool will just pass on to the controller, oh, it's time to draw when I say it's time to draw. There's a mouse down, mouse move, that kind of stuff that it'll say, oh, when I'm the tool, I'm going to control what mouse down and mouse move and all that stuff means, right? So each different tool can do that, and a selection tool will say, oh, you're the selected thing. I might tell you to have some handles on you that I can then grab around and do things to. So that works, and that's not really complicated. I mean, there's code out there, and if you're interested, you can ask questions about it, but it's really not that complicated once you understand the concept. And so, for example, right, the drawing controller just uses the tools. So you have an active tool, and when mouse move or mouse up or whatever happens, you just pass that on to the tool. And the tool does your work. So you're basically setting the context of what's going on in your controller by which tool is active. And then the idea of handles. Handles will then do things, right? So if you click on a handle and you move it, what is it going to do? Right? It might be a handle on the side of a deck, and it moves the deck. It might be a handle on the corner of a triangle, and it moves the corner of the triangle. Right? So all these different handles will do the right thing to the underlying object. So as we look at that, finally, Ward says, this locator is a point substitute that knows how to propagate changes between related figures. For example, when a line connects to a corner of a box figure, and the box figure moves, an updated message propagates through a locator to the line. He later goes on to say, I actually never created one of those in the original HotDraw. But what's really interesting is this is the key to a lot of stuff if you want to build a direct manipulation thing that's actually manipulating something, because probably geometry is going to come into play, right? So the key point about points, right, is that geometry is the foundation of many domains, right? It's not just the foundation for drawing, right? Geometry is the foundation for all these things. It's the point in common with drawings of all sorts. And it's the connection to many black boxes, right? If you've done any kind of programming before, you know there's these things called browser events. They are created for you whether you want them to or not, right? And somewhere in there you'll find X's and Y's and things. Some of them will be meaningful to you, right? But there's stuff, but there's going to be X's and Y's in there, right? There's going to be geometric concepts in these things. If you're doing something on an iOS system, there are going to be gestures, and they're going to have geometry in those gestures, right? And by the way, if you're always figuring out how am I going to test my graphics, I really don't want to test what's on the screen. That's really hard. Or you can do it, but it's kind of stupid. You know what I mean? It's like I'm going to take images and then compare this image versus that image, and there's times to do that, but most of the time you don't want to do that. You just want to know that I'm expecting something to show up at this point, or I'm expecting, something this point to get moved, right? I'm expecting something to move in geographic space. And that's really what you want to test, right? And if somewhere along the line that thing gets turned into something that shows up on the screen, you trust that those primitives are actually going to work. And when they don't, you Google Stack Overflow and you try to find out why not, right? But that's really the thing you want. So within that, let's talk about points a little bit more. And I'm going to use a pun on word all this time. What's the point of self-encapsulation and lazy initialization? These are two concepts that a lot of folks don't even get. Right? They've been using object-oriented languages, they don't understand these concepts and or when to use them and how powerful they really are. So I want to talk about that a little bit, and you'll see how all of a sudden this thing that looks really cool, all of a sudden, wow, this really makes sense. There's just like, if I use these concepts, right, I can build deck builders and all kinds of other stuff, right? So let's look at that. Object properties versus functions. So I have a point, right? And we learned about this in high school math. Boy, this is an appropriate place to be for this, right? You have an X and a Y axis, and you have a point. Of course, in your computer language, they do things to you like flip the axis on you, right? But it's still a point, right? They just flip the axis on you. Okay, but it's still, other than that, it's still X and Y, right? So, the natural thing to do, is, any JavaScript tutorial will show you, you do something like this. You create an object with an X and a Y, right? And there you go, you have a point. What more do you possibly need? Well, the thing you possibly need is how to draw something there. So now I've got to, if I want to actually draw that point or represent that somehow, I got to call some other primitive to draw a circle. And of course, you draw a circle by drawing an arc. But that's the low-line primitive. So I want to draw that circle using the canvas context that I get from using HTML5 Canvas. And I have to get that point. I just ask for the X and Y. I give it a radius that I got from wherever I decided to get it from. And say, draw an arc from 0 to 2 pi. Right? And it works. It's cool. But what if instead you said, you know what? This point is more meaningful than just an X and a Y. I want to do stuff with points. So I write this way, and I create this class called point, and then I have something like this where I can ask the point for its X and its Y by sending a function. And you look at that and say, well, that didn't get you anything. In fact, it's more keystrokes. You have to put this open and close paren, right? What's the point of doing that? The point is encapsulation, right? So I might create this point, and I say, okay, I have an X and a Y, and yeah, I got to keep track of that X and a Y. But instead of letting people just take my X and Y and do stuff to it, or assume that it's there, I'm going to hide that from them, right? Encapsulation is this really great concept that people should learn, right? Because they tend to not. They think of objects as a bunch of properties, right? And in fact, a lot of your JavaScript tutorials are talking about objects as a bunch of properties, and every once in a while you throw a function in there, right? So I make this prototype for point, and I can create a function that returns X and Y. Again, it's like, well, why do that, right? What's the point? We know there's an X and a Y on a point. Yeah, but what if I want to have a polar coordinate instead? A polar coordinate is also a point, kind of, right? And you want to figure out how to draw a polar coordinate. Guess what? There's no primitive that says, draw a polar coordinate for me. There's something that says, give me the X and Y you want me to draw this at, right? So I have a polar coordinate, I have an R and a theta. But I want to figure out what the X and the Y are in order to draw it, right? So now if I have two things I want to draw, I don't have to know whether it's a point or a polar coordinate. I just say, hey, call the X function and call the Y function, and it all works, right? Well, that's pretty simple. But yeah, do I really have just points and polar coordinates? No, it's actually way more complicated than that when you start thinking about stuff you want to build. I have an edge relative locator. Right? I have an edge relative locator that says, I'm this far along this line. And that point along this line is really important to me. And when I have to draw, guess what? I need the X and the Y. Right? So now I figure out this part. And if you keep going, you can realize, and you start drawing this stuff, you start saying, man, this is really slow. I'm calculating X and Y's all over the place. Right? So what's the best way to speed up things? Cache them, right? You make sure you don't calculate them 17,000 times if you're drawing a screen and dragging things across a screen. So a simple way to do that is just introduce the concept of lazy initialization, which you can do if you use encapsulation, right? The idea of lazy initialization says, oh, the first time I call X, if I haven't calculated X, calculate it, and if I have, just use it. Right? So now all of a sudden I'm dragging something across the screen and everything that hasn't changed stays the same, and it's pretty fast. And you saw the stuff I dragged across the screen, that was all pretty fast, all in JavaScript. Right? And that wasn't just drawing one X and Y, right? That was drawing lots of them in order to draw that deck. So also we introduced this concept of lazy initialization, and boy, we used encapsulation to allow me to do all different kinds of things that give me an X and a Y, all kinds of locators. And then we add lazy initialization, that gave me my speed. So I made it run, and I made it right in that it's now a concept rather than somebody with properties. And now I've made it fast by lazy initialization. So, we look at this, objects, inheritance, and prototypes. And really what we just did here, we just did a simple version of it, but we've got a lot more locators. Right? We make a locator or class or prototype with all the methods you want. Make it the prototype or a mix-in for all the specific types of locators. And always refer to properties by calling the functions. Or in the world of Smalltalk, you would say you send a message. We call functions, but I think of them as sending messages. I'm saying, give me an X, give me a Y. And if you think about it as sending messages, all of a sudden this makes sense. Yeah, you don't go in there and say, here, I'm taking your X and I'm taking your Y. I know you have them. Right? It's, give me it. So this is self-encapsulation, actually, is that I even do this to myself. And if you look at that, I can have this message. Now I want to add 2 points together. I'd like to say plus, but you can't do that in Smalltalk yet, in JavaScript yet. So I have to add 2 points together. I don't really want to add 2 points together. I want to add 2 locators together. 2 things that can give me an X and a Y. Right? So if I do this, I have no self-encapsulation. I'm assuming that that guy has a property called X. And I'm assuming this guy has a property called X. So if instead I use self-encapsulation, I say, oh, well, when you're done, give me a point where these 2 X's have been added up. Or if I really want to get fancy, I can encapsulate it further and say, I don't even know what this thing's going to be when I'm done, but it's a thing that gives me an X and a Y, so I'll just create a new function for each of those X and Y's, which will call those 2 X's and Y's, and it'll give me a new object that's just it's a kind of locator. Right? So don't try this at home, we're trained professionals here. But here's a list of the locators we came up with in building the DEX object, the DEX project. Right? Edge intersection locators. Those are important. Where do these 2 things intersect? Right? Edge relative locators, which is somewhere along, some fixed amount along an edge, or some relative point along the edge, proportional. I want to go halfway across this thing. Where's the halfway point? Normal to edge locator. This was a huge one. Because guess what? If you're taking a joist and you want to put a joist next to another joist, you got to figure out, where does that go? Well, I know where this part of the joist is. I want to go normal to that line, right, and some offset of it. So I've got these normals to edges, and all of a sudden I can say, where is the thing that's normal to the edge? I want to, give me an inch and a half away from that thing, right? And it'll just figure it out. And of course, simple point, polar coordinates, and relative locators. This thing is close to that thing, offset by an X and a Y. And then, of course, we had to do the 3D part. So you add other locators where Z matters, right? So you can say, okay, this is close to that, but in a different relative Z place. Or I can say, let me take a 3D thing, and I want to show the front of that, which is basically saying, give me the X and the Z coordination, or the Y and the Z. Right? So you can take a 3D point and just say, hey, I want to take that 3D point and turn it to the coordinates I care about right now, right? So we can switch that around. Or a 3-source relative locator. It's like, I'm getting my X from this, I'm getting my Y from that, and I'm getting my Z from the other thing. Right? So we came up with a lot of those things. And then, of course, you have these other geometric models, like an edge, right? Which is a line with a beginning and end. A relative edge, some portion of that. Of course, polygons come in really handy. Rectangles, circles, and then in the 3D world, cubes. This is a really cool thing. This extruded polygon, we use it all over the place. Right? You get a polygon, you extrude it, and now all of a sudden it's 3D. And a triangle mesh is what you need to draw anything in 3D. So we did all that stuff. And eventually, you look at these things, and we have figures that actually draw those things. And the figures aren't necessarily a one-to-one correspondence to the geometric objects because, for example, we have a closed shape figure. We don't care what the shape is. We don't care if it's a circle or a rectangle or a polygon, we just say, do stuff to the underlying closed shape, right? And that'll work. But he knows whether something's contained, but he just passes that on to the shape. He knows whether, if I want to move it, I move the shape. The shape knows how to move itself. I don't care, right? And then the figure will say, where would I put handles on there? So let's see. So yeah, we just added a couple of methods, handy methods to the rendering context prototype, which you can just go in there, grab that prototype and say, I'm going to add a couple methods because I'm tired of saying draw an arc. I want to draw a circle. So we just added a draw circle method, right? And then we made a circle figure that can know how to call the circle thing. So anyway, you just add that geometry to it as you need it. And so our domain model uses geometry, right? Deck frames are derived from n set of locators, which might be relative to some other reference locator, for example, the corner of a house, right? We had this material specs tell us what type of material to use and supplies the dimensions. So guess what? There's standard things in deck building, 2x10s, 2x4s, 2x8s, 2x6s, 1x4s, 1x5 quarters, which is not quite 5 quarters, but right. So, and then we have joists and boards and posts can be placed in simple formulas, right? They can be placed with simple formulas using locators and the material specs, right? So I say I want a 2x4, it's located over here and it's using this spec, and then I can draw all the rest of the stuff I need. So how do you do that? Put it all together. So what does this look like? Okay, so we follow the idea we're doing test-driven development. So we use Jasmine for our testing environment. And I think somebody else is talking. There you go. Elliot's talking about test-driven development. So this will be just a little taste of that. But we said, okay, before we test this, we want to test a rectangle attached to a rectangular deck attached to a house. So we describe this. We create a deck and we create a house, right? And so actually, in our world, we're because we're designing decks, the house is actually kind of an ornament, right? It's an important thing. We're going to attach it to the house, but we're not designing a house. We're designing a deck, right? So we have this thing called a rectangular house frame. And you give it a width and a height, and it just says, okay, we're assuming you have a boring house that's this rectangular. But it doesn't really matter right now, right? Because we're only adding it to one section of it. So your house could be very, doing something else, but we're just going to attach it to the house. And so it creates this thing, and you just give it a frame and a width, and it creates a reference point at 0, 0, because when you're building a deck, you don't care exactly where your geospatial house is. You just care where the corner of the house is. So that's the origin for us. So we create that, and by the way, each of the vertices are just a relative locator from that point, right? So these relative locators come in really handy. And I have a reference point. So by the way, guess what? If I want to move the house, I have to move one reference point, and everything else moves. All right, that's kind of cool. So I create that frame, and we should have called it shape, but we called it frame. And so that happens when I created the house. And again, I have that reference point, and conceptually, this is what I have now, right? The house is represented by 4 vertices that are 4 locators. It has a few other properties. And now I add a deck frame. And again, we're smart. We said, okay, the house is behind the deck, so the house goes that way, right? And the deck goes this way. But we basically create relative locators for that rectangular deck frame. Right? He looks very similar, only different, because again, he's going in the opposite direction. So they have those relative locators, and so I add those two things together, and now I say, okay, let's take that rectangular deck frame and move it by 24 in the x direction, 0 in the y direction, and he's just going to go do that, and he just tells his locators to move. That's what's happening. And we actually answer whether he moved or not, because sometimes you might want to have a constraint that keeps him from moving. So we do that, and lo and behold, conceptually, this is what happened, right? I haven't drawn anything, right? I'm not worrying about what shows up on the screen yet. I've got these concepts, right? So I now have those locators. And then I say, oh, by the way, I might want to see if these guys are attached to each other. So I do the check attachments. That's for a whole nother talk, how we do that, right? But it then says, oh, okay, I'm going to actually make these attachments. And by the way, what it does in that is says, okay, so now this guy's reference point is relative to that guy's reference point, and they're now attached, right? And that happens, right? So we look at all that, and that's what's happening down here. There's the code, right? I set the reference point to the relative locator, and it all works. So then I want to start testing things, all right? So what happens if I move the lower edge of the house down? Well, man, I want the deck to move down too, right? Does that work? Sure enough, it works. Right? We run our tests and they pass, and that's cool, but we're basically trying to make sure that that's what's happening, right? Again, we haven't drawn a single thing. But guess what happens? If you draw this now, it's going to be in the right spot, right? Because we tested the geometry, right? And we know that this Canvas stuff can draw the geometries that we give it. So all of a sudden that works. So there it goes. It worked. Let's move on. So, so we have this thing called a controller, and so we built our, we might have set up our house just like that, and we have this thing called a controller. So the controller just has a deck and a top view and a canvas. And so that's got to be complicated, right? So it's really not, let me see. So do we have this deck, right? This deck drawing. Remember we talked about HotDraw just has a drawing? Well, we're just smart. We know we're in the deck domain. We're going to have a deck drawing. He's a subclass of drawing. He just happens to know that he has components that happen to be decks. Doesn't actually do a whole lot of other stuff other than create this default figures, which is figure out all the components of the deck, and for each of those components, give me a figure, right? And he does that. So now he's manipulating the figures, but those figures know about their underlying models. And so how we test that? So, when we create that deck view controller, it's really simple, right? On load, we go out and find the canvas that we care about. In this case, we're doing it by looking for the element called top view. And that element called top view is our canvas. That's our view, right? And then I have, if we actually get one of those, right, create myself a deck, add it to the thing, right? And that's where I start up my deck view controller. And then tell it to draw. So now he's off, right? He's out there and he's off. And that controller's now hanging out and can be used, and that controller does a couple of cool things. So the canvas, again, is just an element that allows you to draw on it. The drawing, our model, holds the figures. Our controller captures the events and manipulates the view. Or does it? So let's look at what it does. Pretty simple thing. Again, you give it a drawing, a canvas, and we actually threw in some visible layers so we know what we actually want to display, whether we want to show the deck or not. But he draws himself pretty simply by just telling, he calls a private draw message, which basically just tells the deck drawing to draw itself. But this thing over here, he initializes the mouse observers. And that mouse observer is saying, okay, when these events come, do something and call mouse down, or whatever else I'm going to call. Okay? So because I've separated these two things out, I have some cool stuff happen. By the way, if there's no canvas, I don't initialize the mouse observers. And therefore, the drawing never happens. right? So I don't initialize the mouse observers, and I don't do the drawing, but I do everything else, right? So now, drawing and the figures are really the things being manipulated, and I can do something like strip out that position from the observers and start testing what happens when the mouse goes down. What happens when the mouse goes up? What happens if I move the mouse from here to there? I'm now calling the methods mouse down, mouse move, mouse up, and I can test all that, right? I don't know what the event is. I mean, I don't have to have a browser, right? I don't have the event because I have this thin seam that says turn events into method calls that are mouse down, mouse up, mouse whatever, and I can test them anytime I want, right? So I simply create a controller outside of any HTML element, and I test what happens when you send those pseudo events, right? So for example, I can test my controller. I say, okay, make sure the active tool is there. That's pretty boring. But then I go to the active tool and say, okay, I have a selection tool. Suppose I have a drawing of a canvas out there, and the mouse goes down at a particular point. What happens? I can test that, right? The mouse moves at a particular point. I can test that, right? It happens on a handle. Somebody hits a handle. I can test that. So what happens if somebody gets the handle and moves it by a certain amount, right? Where does that go? I can do all of that. So that's cool. So you might look at that and say, okay, great. So when are the bands and the joists and the surface boards and all that kind of stuff created? When the deck frame figure needs to draw them, because again, we use lazy initialization to create the figures. Right? So I do something like this. I ask the deck frame for its bands, and for each of the bands I make a figure. And when a significant changes occurs in the deck frame, size or shape or whatever, I just trash them. Right? I'm not really getting rid of lumber. I'm just getting rid of virtual lumber. Right? It'd be very expensive if you did this when you're actually building a deck. Right? But it's not in software. Right? So we say, you know what? We just reshape the deck. And when reshaping the deck has the rules of, oh, if I'm this big, I need an extra band. If I'm this big, I need posts and beams. If I'm this big, I need this many joists. So we said, okay, great. Let's just get rid of those and start over, because I just changed the size of this thing. We'll just start over. So as you saw me dragging those things, that's what it was doing. It was trashing the deck every time. You didn't know it was trashing the deck, right? Because all the deck had is a size, right? So I changed it, rebuild all that stuff, use lazy initialization, and here's an example of that. Right? If I ask the deck frame for its bands, he's using lazy initialization. Right? If I have bands, if I don't have bands, go create them based on how big I am. Right? And he just creates a band in the middle of that stuff. And he happens to use the material spec that we're using at that point in time. So if we decide, you know what, we're going to change our deck from using 2x10s to using 2x12s, cool, no problem. We just change it. It automatically happens, because the next time I trash the bands, next time I ask for them, they're the right size. Right? Let's see. Yeah, and there's a band, and the band, again, he just has vertices, right? Nothing about drawing. He just knows where his vertices are, and he'll use all our special locators to make it happen. Materials. Actually, we find that all our materials are basically extruded polygons at the end of the day. Right? A board, a joist, they're all just extruded polygons. So we end up having a material class that takes advantage of that thing. And also, you can turn it into a 3D shape, and it'll go off and do that. And you can also, once you have that 3D shape, you can figure out, oh, what happens when I only want to see the X and the Z portion of it. What happens if I want to see the Y and the Z portion of it? It all happens in one place, and it just magically happens, right? So when we're looking at this deck again, right? We said the house has several properties, including relative vertices, and the frame does too, right? Again, that frame does too. So how does it work? When I create that band, I'm starting out with those two locators. and I have a material spec, and I just create 4 normal to edge locators to figure out where the corners of the band are, right? And I can do the same thing for my joists, right? So when I have a joist, I start out by having 2 bands, and I say, okay, I want to start my joist in between those bands, so I calculate where those things are, and they just magically show up, right? So due to the lazy initialization, by the way, when I'm doing that and drawing that in 2D, there's no reason to ask for the 3D version. I don't need it, right? So I'm not actually changing my 3D view when I'm manipulating my 2D view. But when I ask for my 3D view, now I get it, right? And it'll then create the 3D things that I need, right? So only the X and the Y vertices are used to draw things when I'm using my top view. The top view only cares about the Z coordinate for layering, deciding who to show on top of whom. The Z coordinate may have been needed when attaching components to figure out, okay, this thing is actually attaching at a different spot. But again, I'm not doing it in 3D. I'm just saying that's where that Z is going to, that's where that board's going to go, a little bit lower. And once the material is located, it can then be extruded to 3D on demand. Any 2D perspectives can be retrieved on demand. The same locators and shapes can be used to draw the perspective, whether it's on a canvas or in a PDF. Remember we showed you the PDF that we're generating? We use PDF Kit. It uses the same geometry. It doesn't use the same calls, right? Because different primitives for drawing a PDF than it is to draw to a canvas. But it was actually something, when we added the blueprints, the initial prototype took us 1 night. We had a PDF Kit, said, oh, we already got the shapes, how do I draw those shapes? Right? We've had to add a few other things because there's things on the blueprint that don't show up on the canvas, but it was really simple. And then when we did the WebGL, same thing. Same shape, we added that. I think the initial 3D thing took us about 2 days because we had the shape. And then if we wanted to, we could say, you know, why don't we just draw that in SVG? Well, no reason we couldn't. Of course, why need SVG since we're using the canvas? And canvas is underlying the SVG anyway. Right, so at the end of the day, JavaScript, when used as an OO language, can really build very powerful models. Right? And you want to leverage encapsulation, leverage polymorphism, and leverage lazy initialization. And all these things come together. And if the geometric concepts are realized, models can be rendered in all kinds of ways, as we just pointed out. And last but not least, the DOM and the event handling can be a thin veneer so you can test everything else. That's all I have. You're welcome to ask any questions or whatever. I'll be here at least for the rest of the morning, probably sometime into the afternoon. So, thanks.